Greetings from High Love Grand Park overlooking scenic Westfield. It's my solution to question 8.24. Well guys, in this question here, we are looking at how can you determine if a sample that you have obtained randomly is truly representative of your overall population. So the idea here is to consider a large random sample of 1,500 adults under the condition that 12% of the population is in fact Black adults. How likely then is it for us to get different counts of Black adults in our random sample? So here's the expected count of Black adults that we would get, n times p, 1,500 times the 0.12, that's 180. And here's the standard deviation, again, the square root of n times p times 1 minus p. That standard deviation comes out to be about 12.6. So if we have around 180 Black adults in our sample, give or take 12.6, then we have a pretty reasonable idea that our sample is representative, at least in terms of the count of Black adults of the overall population. So the question then in part B is to consider what's the likelihood that that count in our sample is between 165 and 195. Our job is to use the normal approximation to come up with this probability. So the first thing, don't worry about the word between in this context. So I don't have to worry about whether I'm using less than or equal to in this context, because ultimately we're not going to look at these discrete counts. Instead, we're going to change these into z-scores and use the continuous normal density function. So we're not going to have to worry about the 165 and the 195 specifically. They will just become our boundaries. So what are the conditions for making sure that the normal approximation is a reasonably good fit here for our probabilities? So what you want to look at is the expected value, or the number of successes. That would be n times p. If the expected value here, or n times p, is greater than or equal to 10, and certainly ours is, then that's one of the conditions for indicating that the normal approximation here is reasonable. The other thing that you want to check, you want to take a look at n times 1 minus p. So n times 1 minus p is the count of failures. So we have 1,500 times 1 minus the 0.12. So we're looking to see if that is also greater than or equal to 10. So that's just 1,500 times the 0.88. This is the number of failures that we would expect, and that's 1,320. Of course, you didn't have to work too hard to count that, because you could have just taken the 180 and subtracted it from the number of trials. 1,500 take away 180 gives you the 1,320. That's certainly greater than or equal to 10 also. So if these two conditions are met, then the normal approximation is reasonable in order for us to calculate this probability. Let me take just a second though and show you, give you some idea intuitively of why that calculation n times p and n times 1 minus p, why having those greater than or equal to 10 is valuable. So let's go take a look at the calculator. This is what I've done here. Let's see here. Got to go grab it down here. Here we go. So you may recognize this graph. This is the graph of the probabilities where I am, again, shooting 20 free throws. My success probability is 0.4. And what we've graphed here are the 21 probabilities. The 21 probabilities starting with the counts 0 to 20. So I make 0 free throws way over here, all the way to the likelihood that I make 20 free throws way over here. Now notice, in this context, the normal approximation wouldn't be quite so good. N times p, 20 times my success probability of 0.4, that's only going to be 8. And notice I can see that 8 right here. 8 is the expected value. That's, if you will, the center here, or if you will, the peak of our approaching. It's not exactly a normal bell shape here, but we're getting closer to it. So understand the problem with considering this a normal shape is because we have different sized tails. So on the right side of this curve, we have a tail that's much longer. On the left side of the curve, we have a tail that's much shorter. And part of the problem is because we're essentially centering our distribution around 0.8, not 0.8, but rather around a success count of 8. So if we can get our success count a little higher than that, so if we can get our success count to be 10 or higher, the idea is that both of the tails will essentially be long enough that we can use normal calculations, we can use normal probabilities to approximate these. So essentially, we want to get the count of successes and the count of failures high enough to shift this graph over so that we have tails on both sides of the distribution, because in fact, the normal density function has two tails that are exactly symmetric on both sides of that distribution. So we need to make sure that n times p and n times 1 minus p are at least 10 or above. That's what's going to get us essentially the shape we need, that bell shape that we need. So let's look at the specific calculations here then in this context. So I want to turn the 165 and the 195 into z-scores. Of course, I've already calculated the mean and the standard deviation, so that helps. We're nearly done. You should always set up the calculation. So the 165, take away the mean of 180. Then I can divide by the 12.6. That gives me a z-score of approximately negative 1.19. And then I also have an upper boundary here, the 195, take away the same mean that we calculated of 180, dividing by that same standard deviation that we calculated of 12.6. That gives us 1.19. So now I can change this from a probability about counts, I can change this to a probability about z-scores. So I would offer that showing your work this way is important. So my lower boundary is negative 1.19, and I'm looking for the likelihood of z-scores in between those two boundaries, the negative 1.19 and the positive 1.19. So here we can go and calculate the normal CDF. We can use that to actually do this calculation. So go to our home screen. We'll call up normal CDF here. So second button, variables button, normal CDF should be the second option. Our lower boundary is negative 1.99, or excuse me, negative 1.19. The upper boundary is positive 1.19. Again, because we're using z-scores, we don't have to mess with mu or sigma. We don't have to mess with the mean or standard deviation. The mean of z-scores is 0. The standard deviation is 1. So there we go. About 0.77, we'll call it. So what have we accomplished here? What this says, with the probability of about 0.77, this says that using this sampling procedure, if I have a random sample under the condition that the actual percentage of black adults in America is around 12%, what I would expect about 77% of the time, or about 3/4 of the time, typically I would get then counts between 165 and 195. Again, when I say typically, I mean about 75% of the time. So if I am looking at my random sample, and in my random sample, if my count actually falls between 165 and 195, then that looks like it reasonably represents the population, because I should get something like that around 3/4 of the time, under the assumption that 12% of the population is in fact a black adult. That's what's going on in question 8.24.